Good morning. So, yesterday we discussed about the type of ignition considering both charring as well as non-charring type of solid fuels. Wood, which is an example of charring fuel, and polyethylene is then example of the non-charring fuel. Wood is a heterogeneous solid because it contains moisture, liquid water will be there present inside that, volatiles which are trapped gases of different composition, then solid carbon and then another solid which is inert mineral which is called ash. So, now even though it contains these materials, it is intact as a single solid piece, but if you heat it upon subject to different temperatures, these components will come out. When you heat it to about 100 degrees, the moisture comes out, and in the range of 350 to 400 degrees, the volatiles come out and so on. The volatiles are the gases which has fuel components also. See, for example, volatiles can have CO2, CO, N2, O2, CH4, then C2H2, C2H4 and so on. There are several components. The composition of these components will be different, and as the temperature increases, this composition also will change. So, it is, as I told you in the beginning, it is not like evaporation of a liquid fuel where its own vapor comes out, and the composition of the vapor will be same as that of the liquid. If it is a multi-component liquid, then the composition, the vapor phase and the liquid phase will be different, but we can say these are the two constituents. But here the composition will change, even the constituent can also change a little bit. So, the devolatilization or release of volatiles start when the temperature of the wood becomes higher than say 350 degrees centigrade. These volatiles have fuel components, say CO, CH4, even H2, very important component, then C2H4 etc. This fuel components mix with the ambient air and it forms a mixture within the flammability limit. Basically, we are talking about the mixture reaching the lower flammability limit, so that when you introduce a pilot flame, then ignition occurs. So, piloted ignition is possible. Okay. So, I have a solid wood piece and I heat it externally, temperature increases and some volatiles come out, a mixture is formed with atmospheric air. Then when you ignite this, a flame forms. So, piloted ignition is possible. Now, as I told yesterday or in the previous class, when the temperature of the surface increases beyond say 400 degrees and reach a temperature say 800 degrees etc., the volatile gases which are coming out will be at higher temperature, and the mixture which is formed in the gas phase will also have a higher temperature. If that temperature exceeds a temperature called auto ignition temperature, then without aid of a pilot ignition, the mixture can ignite. So, auto ignition is possible in this case. So, we were also talking about see the wood, when volatiles go out, moisture first goes out, volatiles goes out next, then solid carbon and inert material ash will be remaining. These together is called char. See, this together is called char, and when the solid is heated up, see this is wood layer, when it is heated up, so let us say that it is heated up to some level, so that a layer of char is formed. So, this is the char layer, and temperature of this char layer can increase. If it increases to a temperature around 900 degrees centigrade, 850, 900 etc., then oxygen from the ambient can come to the surface and surface reaction can take place, which is actually indicated by a glowing ignition or a radiant red color surface. Hot surface which is red in color will be visible. Now, this will also heat up the raw wood which is present beneath this char layer, and volatile can be released. This volatile passing through a hot char layer will be hot with a high temperature, then the mixture which is formed will auto ignite. So, you can see that this is not just like a liquid evaporation where the vapor component comes out. Definitely we need a pilot ignition there, because normally the boiling points of the liquid fuel will not be more than the auto ignition temperature of the liquid fuels. So, and also we have seen that upon heating from the top, the maximum temperature the surface liquid surface can attain is the boiling point. So, in this case you can see that there is no limit for the temperature of the solid surface, and the solid can be heated up to higher temperatures also. In fact, when the surface reaction take place, the temperature can increase beyond 900 degrees, it may go to 1100 degrees also. So, in these cases what the volatiles which are coming out can auto ignite. So, pilot ignition and auto ignition are possible in the charring type of fuel. Going to the polymers or non-charring type of solids, where say polymer basically like PMMA or polyethylene etc. will not produce a carbonaceous residue. It may have some impurities, but it will just upon heating will devolatilize. That means it may melt or it may sublimate to produce the vapors. Okay, now the hot plastic can soften. Polymers or plastics, so it will soften. So, there is a temperature which is called softening temperature. Similarly, there is a melting point for this. So, melting temperature. Pyrolysis temperature will be there, which need not be same as these two, one of these two, it may be different. So, pyrolysis temperature is one where the gases will come out either due to melting and vaporization or due to sublimation. Where exactly what happens is the polymer will produce its monomer and it can do, or there may be some multiple component coming out of the plastics or the solid non-charring solid. So, pure monomer alone need not come out, because the pure monomer also can decompose and multi-component gases can come out. So, in this case also you will see that predominantly piloted ignition is possible, but if the gas environment etc. is at high temperature, then auto ignition is also possible. But predominantly the temperatures what we are talking about, the pyrolysis temperature etc. cannot be more than the auto ignition temperature for the fuel gases which are coming out. So, we normally go for piloted ignition in these cases, or auto ignition can occur only when the ambient is at a temperature more than the auto ignition temperature. So, this we have seen. Now, let us see some experiment which is done in a say conical heater, the cone calorimeter. Okay, there is a radiative, this is the surface of the solid. So, this is surface of the solid, and there is a radiative heat flux which is imparted by a cone heater, and from the surface of the solid I keep a source spark at a certain distance as per the standards. Now, what happens is this is the surface which is heated up. So, locally I keep a spark here at this particular point. So, now what happens, the gases comes out, volatile gases or the devolatilization gases comes out, pyrolysate what we call that, and form a mixture. Now, this mixture should be more than the lower flammability limit, and this piloted ignition will cause a flash. What is flash? Instantaneous flame, which is premixed flame, but it will not continue, it will just produce a flash, and the flash will, once this mixture is consumed, the flash will disappear. Okay, now we have to wait for some more time for a set of gases again to come out and form another mixture, again which is ignited, then another flash will produce. But in this period, the surface is also getting heated up to higher and higher temperatures. Okay, there is a minimum temperature at which some gases are coming out, a flash is produced because of a flammable mixture formed over the surface and being ignited by the spark. Now, more and more rise in the surface temperature will cause more and more volatiles to be released. Okay, the volatile release will start, say for example for wood at 350 degrees centigrade, but when you increase the temperature to 500 etc., what happens is more and more heat up will happen and the more and more volatile will release. So, at one particular stage, lot of vapor will be available and it will have a good volume of vapor or the gases and the air mixture, and the spark will ignite to form a sustained ignition. That is a diffusion flame now forms over the solid. So, here you can see a diffusion flame forms over the solid, where the volatile gases from the surface goes and feeds the flame and the oxygen from the ambient comes to the flame from the ambient side, and this is sustained. Now, the spark can be removed because now the surface is hot enough such that the volatile gases are released at a continuous manner, unlike the flash which is instantaneous flame. Once it forms, then we need to wait for some more time for the flash to form again, because vapors on the volatile gases on the surface to reach this gas phase and form a mixture again. So, multiple flashes can form before a sustained ignition can occur. So, we give an example here. So, please see that the solid fuel ignition is not so straightforward as the liquid fuel ignition. Liquid fuel ignition, when the surface of liquid becomes flash point temperature, then a flash is produced, then when it increases to fire point, a fire is produced, that is a diffusion flame is formed. In this case, multiple flashes can form, the surface can reach a temperature much more than the pyrolysis temperature, so that a flame forms over the surface and now it may sustain. This is a case where a wood, again red oak wood sample is being heated. Please understand that I can vary the heat flux. In this particular context, the heat flux is chosen as around 2 watts per centimeter square, and again like it is a cone calorimeter type of experiment where this heat flux is imparted. So, as I told you, the temperature of the wood sample should be like above 350 degrees centigrade to cause volatile release. So, there is no point in seeing temperature below this. So, let us start from a time instant where the temperature of the surface has reached 350 degrees. Now, volatiles get released, some vapors are formed which is mixing from water gases released, they mix with the ambient air. Upon ignition a flash forms, but now the mixture is consumed. Now, I have to wait for certain time period, here say about 50 seconds, so that enough vapor again form, when enough gases come out and enough mixture again forms, another flash is produced. Now, during this time you can see that the surface itself is heated from 350 degrees to about 360 degrees, that is increase in temperature for the surface. Now, between the second flash and third flash, the time interval reduces because more vapor are available within a short duration because of the heat up of the solid surface. Now, third flash forms, then when the heat surface is heated to a temperature of about 372 degrees centigrade, you see a sustained flame forming over the solid. So, multiple flashes form and ignition occurs. So, the time delay, what we call is from the initial temperature, it may be 30 degrees, to what is the time taken for heating up the solid, from that to this, where a sustained flame is formed, that is the ignition delay or time for ignition. Okay. So, the temperature at ignition is 372 and the time for ignition is 749 seconds, 750 seconds. Okay. Now, the measured temperature is 395 degrees at the time of ignition. So, that is within that period the gas phase also is heated up and that is also transferring heat apart from the radiant heat flux which is imparted from the cone calorimeter, correct. So, there is a increase in temperature when there is a sustained flame which is formed. So, this shows how complex is the ignition of solids. The time for ignition depends upon several factors. Okay, now let us consider why we choose this heat flux. If it is higher than this, what would happen, or if it is lower than this, what would happen? If it is, say, first lower than this heat flux, the surface, the solid, we are heating with a particular heat flux. So, this is incident on the solid surface. Now, there is some heat loss and there is some conduction fluxes. So, now the net heat coming in should be more than the losses to the ambient as well as the conduction to the solid. If it is not, then the surface will not be heated up. So, if you reduce this below this, maybe the surface temperature will not increase at all. Here itself it is very slowly increasing. Okay, now as a consequence of higher heat flux, this surface temperature reaches the value of 350 degrees much faster. Do you understand? So, the ignition delay will reduce when you increase the heat flux. Do you understand? So, the ignition delay depends upon the external heat flux, where the sensible heating of the solid from the initial temperature to the pyrolysis temperature or the devolatilization temperature occurs. 350 degrees where it starts basically. Now, what is the another consequence for this particular faster heating? In this case, there is a composition for the volatiles. Volatiles are so these are the volatile constituents, but I do not know what are the percentages of this, volumetric or mass percentages of this. That will vary when you heat it at a faster rate or slower rate. The temperature at which the pyrolysis starts, the 350 degrees, and it may go to about say 400 degrees, that will not vary much. That is the rate at which the heating is done, that will make the wood or the solid sample to reach the pyrolysis temperature faster, but as a consequence the composition of the volatile may change. That is another important thing, okay, because this volatile composition is also dependent on the rate of heating. So, basically what we are trying to emphasize here is the analysis of ignition can be done with just thermal analysis, where we concentrate on how the solid is heated, but to get more knowledge of how much volatiles are released, what are the fuel components in that, composition of that, etc., needs more research. Now, let us talk about, in order to understand the ignition in a more clear manner, we have to talk about what is the effect of conduction heat transfer within the solid, because in all these cases the surface gets the heat, flux, incident heat flux, and the conduction occurs. Okay, let us not even take into account of the losses, heat losses. It may also be there, but let us say this is not taking into account, we will not take into account of this. Whether the conduction to be considered or not in our analysis, if you focus on that point, we will see that the surface temperature, see, let us say this is not very significant, then the surface temperature rise depends upon the incident heat flux as well as the conduction which is happening within the solid. Okay, and surface temperature actually dictates the pyrolysis process or the ignition process, because we have to reach the pyrolysis temperature, which is also called ignition temperature. Pyrolysis temperature and ignition temperature, T pyrolysis is same as T ignition. where a sustained flame is seen. Now, let the thickness of this material, physical thickness, be Tp, and there is a incident heat flux Q dot double dash I, incident heat flux. Now, I can classify the material as thermally thin. Please understand that thermally thin is different than physically thin. The object may be physically thin, say 2 mm sheet, it's physically thin, but it need not be thermally thin. That means still I need to solve the heat transfer within the solid. So, if it is thermally thin, then I need not solve this. So, how will I find whether the solid is thermally thin or not? For that, I have this expression. This is just the conduction heat, conduction. See, for example, what is the temperature rise needed? See, initially let us say T ambient is at low temperature, and that is the initial temperature of the solid itself, and T ignition is the temperature at which pyrolysis or ignition occurs. So, this is the rise in temperature required, and this depends upon the heat conduction in this. Basically, the heat flux comes in and there is a heat which is conducted inside, so the temperature rises. So, you can see this. Basically, Tp is the physical thickness is less than or equal to 2K T ignition minus T infinity by the incident heat flux. Then we can call the solid fuel as thermally thin. So, geometrical thickness also plays a role here. So, if it is less than that, then we can call it thermally thin. When the solid is classified as thermally thin, I need not solve for the conduction inside this. This will be very low. Okay. So, now in this classification, basically I will give an example here. So, this is thermal conductivity, ignition temperature, ambient temperature, incident heat flux, physical thickness. So, now let us say I have a incident heat flux of 10 kilowatt per meter square, and say wood or any other solid, thermal conductivity is 0.15, low thermal conductivity 0.15 watt per meter Kelvin, and let us also see ambient temperature is about 30 degrees, ignition temperature may be 330 degrees, approximately I will say the temperature difference is 300 degrees centigrade. Now, in this context, if you apply this, the physical thickness, if it is around 9 mm, then the solid is classified as thermally thin. So, as I told you, 9 mm is not very thin basically, geometrically, but in this case of low heat flux, even 9 mm thicker solid can be classified as thermally thin. Now, if you increase the heat flux to 50 kilowatt per meter square, from 10, 5 times if you increase, then you will see that the 1.8 mm or about 2 mm sheet also cannot be considered. 2 mm sheet is not thermally thin now, because the criteria now becomes 1.8 mm. So, as the heat flux increases, incident heat flux increases, the conduction also should be taken into account. Okay. Then, to avoid the conduction analysis inside the solid, I need a thinner and thinner material. So, thermally thin is different than the thickness. I cannot say always that if you have a 2 mm sheet, it is thermally thin. It is not required to say mention that, because of the fact that it depends upon what is the heat flux. Okay, now let us try to understand the ignition of a thermally thick solid. So, obviously, as I told you, the ignition problem for solid can be analyzed by just heat transfer analysis in the solid. Okay, what is the heat flux? So, different boundary conditions I will try to give, solving a simple governing equation where a time dependent temperature rise occurs and conduction occurs from the surface to the inner portion of the solids. That is it. Because it is thermally thick, there is no way I can neglect the conduction heat transfer within the solid. So, that is what we have been discussing now. If it is thermally thin, then I do not need to do this. Thermally thin, what I will do is the temperature rise can be equated to some convection loss or some some other type of say H into delta T something like that, I will put and try to solve this. But in this case, the conduction has to be solved. So, I now end up in a governing equation which is the transient term in the left hand side. Rho S is the density of the solid, Cs is the specific heat of the solid, and this is the increase in the temperature with respect to time. So, volumetric term indicating the increase of the internal energy of the solid with time, and this is balanced by the conduction within the solid. That is it. This is the simple governing equation, and it needs, yeah. So, it is partial derivative because T is a function of two independent variables. So, partial derivative equation, partial differentiation equation is coming here, and it requires one initial condition and two boundary conditions, second order space derivative, two boundary conditions, and first order time derivative calls for one initial condition. Okay, now let us take this example here. Initially, the solid at all x time equal to 0 can be at the initial temperature T0, which can be ambient temperature also. So, ambient temperature is T infinity. Okay, that is the initial condition. Then, please understand that normally when I take this, the bottom surface of the solid, that is a thickness here, there is a physical thickness here Tp. The bottom surface of the solid, I can have a Dirichlet condition T equal to say T infinity, let us say, or I can say insulated condition Q dot double dash equal to 0. Some condition I can impart. Similarly, sides also I can give some convective condition or insulated, any condition I can give based upon the problem I am trying to solve. But the part here on the top where the heat flux comes in, I can specify specified heat flux, okay, because of say cone colorimetry experiment, there is a heat flux which is coming to the surface from the cone heater. Then I can also have a flow of hot gas with U infinity, T infinity, etc., which is higher now. Now, this basically will have a convective heat transfer, this T infinity minus Ts, that will be the heat which is transferred to the surface. So, convection can be there. If this H actually depends upon the velocity, conditions, the ambient, etc., correct. So, this how to determine this, again we have correlations for Nusselt number from which I will determine this. Similarly, the radiation also comes. So, this heat flux can be due to radiation also. So, radiation also can come. So, convection plus radiation also can contribute. Do you understand? So, the problem is just a heat transfer problem. Problem to understand ignition of a thermally thick solid is nothing but the heat transfer problem which I solve, where I try to heat up the solid time dependent manner, solving a one dimensional transient conduction equation. Do you understand? So, as I told you, the boundary conditions are important. So, I do not really care about these two sides because it is only one dimensional heat transfer I am solving. This is my x direction now. So, x equal to 0, I have some boundary condition, x equal to surface xx or L, whatever thickness Tp, x equal to Tp, I have this is x equal to 0 here and x equal to Tp there. I have to specify two boundary conditions. Okay. So, when I solve this with some different type of boundary conditions, I can get some analytical solution also, or in most of the cases I will end up solving a numerical, solving this equation numerically. Okay. Let us see the boundary conditions. Constant surface heat flux. So, material Q dot double dash S, that is incident. So, at the interface the boundary condition will be what? This will be equal to the conduction. So, basically here now what I am doing is, here I am putting x equal to 0, x direction is in this direction. Okay. Bottom boundary condition is different. Please understand, this may be T equal to T naught or insulated etc. So, bottom condition is different, but you can see that here at x equal to 0 is now surface. Okay, now whatever flux comes in, I do not take into account of the loss, this is 0. So, whatever comes in the surface is conducted inside. So, based upon this balance, the surface temperature will increase. My objective is to find the rate of increase of the surface temperature due to a given heat flux and conductive heat transfer within the solid from the surface. So, this is the boundary condition I use. Here any other boundary condition. So, two boundary conditions, I am talking about the top boundary condition where the heat is coming into the solid, correct. Now, when there is a flow of, here in this case there is a flow of hot gases, say T infinity, and this is Ts, which is equal to Tx equal to 0, correct. Now, as I told you, here the heat transfer is convective heat transfer, T infinity minus Ts, and that is coming in and that is conducted inside here. This is the conduction. So, in this case also I can say, when if we have some correlations to determine H, this problem is easily solvable. Okay. Then I can say third set of problems. There are several sets, we can have several configurations. I am just discussing a few of them. Here constant heat flux, convective cooling on one side occurs. Okay. Now, here this, there is a constant heat flux which is coming in, combination of these two, let us say. See, one more thing is, there can be some cooling also which can occur, that also can take into account. In this case, basically I have two things. First one is T infinity minus T surface, Tx equal to 0 is T surface. This T infinity is higher because of the convective flow, but what I call as cooling is here. Please understand that this radiative heat transfer, when the surface reaches a particular value, there may be heat loss due to radiation. That is also, so this may be negative value. Okay, so what I am trying to put here is, I now have not only the convective heat transfer coefficient, I have a total heat transfer coefficient, which is the convective heat transfer coefficient plus the radiative heat transfer coefficient. So, when you have these simple boundary conditions, then I can have analytical solutions in the form of error function or inverse error function, etc. Some complicated functions can be used to solve this analytically, or we can solve it numerically.